Hello everyone. In this recording, I will try to answer a question that was submitted to me by one student. And it's a typical question that repeats itself in different forms. So I'm going to try to explain the basic ideas behind this question. I'll try to answer it as well. All right, so let's start. I already wrote the question here. Um, The question says a packet transmission system is designed to send packets through several intermediate stations across a medium that follows these specifications. Um, and we will assume that the signal repeaters are placed as needed and do not introduce any delay. Right. So station 1 to station 2, these are two stations. Between them there is a cable, that multi-pair twisted pair cable, and the distance is 4 kilometers. And from 2 to 3, a multi-pair twisted pair cable over a distance of 2 kilometers. And finally another cable from station 3 to 4 uses coaxial cable over a distance of 9 kilometers. All right, the repeaters introduce zero delay. Assume signal attenuation is fully compensated by the repeaters. The transmission data rate is 1 megabits per second. And we're given a total of 40,000 bits of data must be transmitted, which includes a header of 100 bits. Each packet size is 15,000 bits. Packets must be padded to a full size of 15,000 bits and are retransmitted immediately, i.e., as soon as the last bit of the packet arrives at an intermediate station. And the required is to calculate the total end-to-end delay required to transmit the data. All right. It looks a lot complicated, but it isn't. So let's take a look at each one of these paragraphs and try to understand what it means. Right. So let's begin with the first one here. A packet transmission system is designed to send packets through several intermediate stations. All right, so that's I drew the picture here. Let's assume that we have station station 1, station 2, station 3, and station 4. So these are intermediate stations, and I want to send the traffic in between. Okay, so between brackets there says that assume signal repeaters are placed as needed and do not introduce any delay. So let's explain that, right? All right, so from what you know, I mean, when you send traffic across a cable, there will be attenuation. So to avoid the attenuation or to boost the signal, sometimes we need to place repeaters across a certain distance. So let's say every 1 kilometer or every 5 kilometers or whatever the requirements are. These repeaters are physical devices that take the signal and regenerate it again, boost it, and send it. But they introduce delay. So if I look at traffic between any two stations here, right? So we know that the signal will travel and it won't travel immediately. There will be some propagation delay. So if we say normally the signal will travel from this point here, it won't appear immediately here on the same time. This is time, or actually it progresses the other side. So the time progresses downwards. So this is t0 here, and it progresses downward in this picture, right? So if the signal starts from this point, it will um, appear after a certain time, and the certain time is called propagation time. Excuse my drawing here, it's not accurate. Usually it's like a straight line or as straight as possible. So this is going to be the propagation time. If there are repeaters, like this picture at the top here, what will happen? The signal will tra travel up to the repeater, and the repeater will introduce a delay, so the signal will look like this on the time scale. But since the question says forget about the delay, there is no delay, assume that everything is um, negligible, the delay is negligible. So we're just going to assume the simple case where it's just straight line like this one. So that's the first paragraph here. The second paragraph says, okay, from station 1 to 2, we have a multi-pair twisted pair cable. And the distance is 4 kilometers. So this is the distance from here to here is 4 kilometers. And from here to here, the second one is 2 kilometers. And finally, from here to here is 9 kilometers. All right, why we are mentioning the type of the cable? The type of the cable affect the propagation time, right? Signal travel, or electromagnetic signal travel through space using the speed of light in vacuum. But if we are sending it through any other type of medium, we have to consider the effect of that medium on the speed of light. So usually it's slower, of course. All right, so we will revisit this topic later. Now let's take a look at the third paragraph. Also, the repeaters introduce zero delay, assume signal attenuation is fully compensated by the repeaters. So this means that whatever attenuation happened, when it hits the repeater, everything goes back to where it was, right? And the transmission data rate is 1 megabits per second. So this is how many bits we send per second. Okay. Then what's given? A total of 40,000 bits of data must be transmitted, which includes a header of 100 bits. So if we looked at how network layers work. So the application will send the data to the transport. The transport will add a header and send the data to the network and so on, right? Until the data is actually transmitted over the physical cable, physical link. Here we're saying that whatever, there's no much mention of which layer or which transport or nothing. What we can gather from this paragraph is that we have 40,000 bits of data, and there is a header in that part, 100 bits. So it's the whole thing is 40,000, right? Um, and but it seems like the hint of the second line says that each packet size is 15,000 bits. So this means that we need to split that data into packets and send them. And each packet is 15,000. Packets must be padded to a full size of 15,000 bits. All right, so let's hold on this first and for a second, and let's imagine how things will work, right? Without going into details. So we can figure out that since we have 40,000 bits of data and we need to divide them into 15,000 bits, this means that we will have multiple packets. So if I want to start from station 1 and I want to send the packets, let's use blue here. So I want to send a packet. So packet will start, the first bit will start from here and travel. There is a propagation time. This is TP, right? And then this is the first bit. The blue line represents the first bit, but we don't only have one bit. We have 15,000 bits. So the 15,000 bits will take some time to transmit, and then we will have at the end the last bit. So from here to here, we have this transmission, the TF, or the transmission time. So this the whole frame, and we're going to send them bit by bit until it's over. All right, so here in the question says that packets must be padded, so all of them must be 15,000, and are retransmitted immediately as soon as they reach the intermediate station. So if we consider this blue packet here, as soon as it hits or it arrives completely at station 2, there the station 2 will start sending them to station 3. Again, there is a propagation time, right? And transmission TF, transmission time here. By this time, by the time this is going on, station 1 is sending the second packets and the third packet and so on, right? We still don't know how many packets, but this is the idea, right? And as soon as the packet is completely arrived, not part of it, but the whole thing is arrived, because the station needs to receive the whole packet before it transmits it. So as soon as the second packet arrives completely, and assumed correctly as well, it will be sent by station 2 to 3. And as soon as the third packet arrives, it will be sent as well. All right, what happened when station 3 receives the first packet? It will send it as well, right? And what happened when the second packet arrives? It will send it, and so on. So this is the overall approach to the answer. So we just need to figure out the total time which was required, is required here. The total time from the time we sent the first bit here up to the time where we receive the last bit at the last station, somewhere here, right? So this is what we are looking for. Okay, so now this, we don't really know how many packets yet, but this is the general approach. It could be 2, it could be 3, it could be 4, but this is the general approach. So I'm just going to repeat what we understood so far. We need to understand there is a propagation time, and that's affected by the length of the cable and the type of the cable, right? And then we need to understand there is a frame time, which is affected by the length of the frame, the size of the frame, and the transmission rate, right? And we also need to understand that there will be multiple packets being transmitted. All right, so let's do some calculations. All right, let me erase this. Okay, the first thing I want to know is how many packets we need, all right? Again, don't concern yourself with the type of the packet. Is it IP? Is it TCP? Is it Ethernet? We really, the whole thing here says that each packet size is 15,000 bits, and there is no any other information. We don't know where is the 40,000 bits are coming from. So we don't know. So let's simplify it and say we have 40,000 bits. We want to divide them into 15,000 chunks, right? We'll call them packets. If you have more information in the question, if somebody tells you, well, it's a TCP and it's going to IP, and then from IP it's going to Ethernet, then you have to calculate the header of all of these and the trailer and all of that. But now in this question, we don't really know, and it doesn't matter anyways, because the approach is always the same. So we have 40,000, and we need to divide them into 15,000 bits. So if we take, let's say, I need to calculate the number of packets. So the number of packets is 40,000 bits total divided by 15,000. Right. We will end up, I'm just going to use the calculator here. So 40,000 divided by 15,000. We will end up with 2.7 packets. Now, this means practically we have two full packets. Each one is 15,000 and 2/3 of a packet. Right? But here it says that the packets must be padded to a full size, which means that if I take the 40,000 and divide them, we will end up with one full packet, another full packet, and one packet that has some data, but I'm still gonna fill it with zeros or any other numbers here, random zeros probably, so that we end up with 15, 15, 15k each, right? So the number of packets, regardless of what's the content, is 3, right? So this is equivalent to taking the ceiling of this number and we're getting 3, right? Or rounding up to the nearest integer, right? So we're just rounding up to the nearest integer. Okay, so that's the number of packets. So now I have an idea of the shape or the solution. So I am sending packets. Let's take again the blue color here. I'm sending packets from here to here. This is the first one, and then another, this is the end of the first one. Now I still don't know what the propagation time is, right? But you can figure out that since this is 4K and this is 2 kilometers, then this probably will take twice as much propagation time as the other one. So let's say I am moving this a little bit down here. Again, it may not be accurate representation, so we didn't calculate the times yet. We'll leave that to later. But here's the illustration. So the first one, second packet, third packet. So these are 3 packets. Okay, as soon as packet 1 arrives, again, we assume there are no errors, nothing like that. So station number 2 will send them immediately as per the instructions. And notice the propagation time is shorter here. Okay. So we'll send them, and as soon as the second packet arrives, also we'll send it. And finally the third packet arrives, so we'll send it as well. Okay, now station 3 will repeat exact same thing. It receives the first packet, it sends it. And since this is 9 kilometers, so probably will take some long time to arrive. So the propagation time will be a little bit longer here, right? And again, I will calculate the exact propagation time in a minute. But the idea is as soon as the packet arrives, and I find it always useful if I try to draw the pictures as accurately as possible. I could have calculated the propagation delay ahead of time so that I can get a more accurate picture, but I didn't, so we'll just continue as is. Let me grab this line a little bit down here, so, or maybe if it collaborates a little bit. Here. Okay. Okay, so in order to find the answer, I have to find out the propagation time here and the propagation time. Yes, that's from here to here. Yeah, that's true. And so if you are following, so this is the first bit here and it arrives here. So that's the propagation time, right? And then the first bit sent here and this is the initial time, and this is when it arrived here. So this is the second propagation time. We'll call it TP2 and this is TP1. And for the same reason, we have this propagation time here. So this is TP3. Okay. What is TP1 and what is TP2 and what is TP3? Okay, we have clues. The clue is, well, first is the distance, of course, and the second one is multi-pair twisted pair cable. That indicates what kind of a cable we have. If you go to the book and specifically table 4.1, chapter 4, you will see this table here. And the table tells you, it lists the type of cables and the frequency range that their bandwidth, I mean the frequency bandwidth, and then the attenuation, typical attenuation, typical delay, and the typical repeater spacing. We don't really care about the repeater. We just care about this part here, this column, which is the typical delay. Here, the typical delay for coaxial cable, for example, is 4 microseconds per kilometer. So the signal travels for or takes 4 microseconds to cross 1 kilometer. So if we have 2 kilometers, this means that we need 8 microseconds propagation time and so on. All right, so we have two types of cable. The first one was the multi-pair cable, and the typical delay for it was 5 microsecond, and we have the coaxial cable, and the typical delay for it is 4 microseconds. Okay, so we have the answer here will be, we have 5 microseconds. Just double checking here, it's 5 microsecond for the twisted pair, yes. All right, so 5 microseconds for the first cable, and the distance will be 4 kilometers. 5 microseconds per kilometer. Don't forget that, right? And if you use the units carefully, you will avoid this kind of problem, right? So 5 microseconds multiplied by 4, you get 20 microseconds. That's the propagation time. For the second one, we have 5 microseconds because it's the same type of cable, but the distance is 2, so we will end up with just 10 microseconds, which is perfectly here. If you think about these boxes, each box is 10 microseconds. So here we have 2 boxes, here we have only 1 box. So good drawing here, or good scaling. The last one is this is coaxial cable, and the coaxial cable from the table is 4 microsecond, has 4 microsecond delay per kilometer. And if you're wondering how am I supposed to know that, usually you're given, well, you have the book, But if in the exam, usually you're given this information, right, in a appendix or a crib sheet at the end. The distance is 9 kilometers, so 4 by 9 is 36 microseconds. All right, so this is the propagation time. All right, maybe you should put this aside so we leave some space. So I'm just gonna copy it, put it aside here. Okay, now we need to know the distance. This, it's not a distance, it's time. This TF. Okay, the TF, the time it takes a whole frame or a packet to go from one end to another, is really the size of the packet, let's call it L here, and the transmission rate. The size of the packet was given to us, it's 15,000, right? So, and it doesn't matter which cable, it's always the transmission rate is always the same. So we have 15,000 divided by also given to us 15 megabits per second, the transmission rate. So that's one, it's a million. So 1 multiplied by 10 to the power of 6. All right, and this will be, if I do the math here, this will be 15,000 divided by 1 million. That's seconds, so that's 0.015 seconds, or multiplied by 1,000, so you end up with 15 milliseconds. All right, so that's what we need now to calculate the whole thing. So the only problem I see is this: we have milliseconds here and microseconds here, so we need to convert one or the other. So I can multiply that by 1,000, so we end up with 15,000 microseconds. But I would rather convert these to milliseconds, or the propagation time to milliseconds instead. So anyways, let's put this, also put it aside. All right, now we need to calculate the whole time, as I mentioned earlier, from the beginning here, from the, actually from, if you follow, you see that from here, we'll do a dotted line from here. So this is the T0 until we end up with here. We need to find out the time. Okay, if we look carefully, we'll see that it's actually, we know most of it, or all of it actually. So let's let me draw a line here, if I can make it dotted. Maybe I can't. All right, so maybe I'll use some other approach here. Let's use red again and try to be as steady as possible. So if you look at this point here that I am pointing out at, you see there is the total time equal, first is TP1, right? Plus TF, right, up to here. And then from here, we have TP2 plus TF, right, from here to here, TP2 and TF. Okay, and then let's do this again. So we have here TP3 and TF, 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 three TFs, right? So that's TP3 propagation time from 3 to 4 plus 3 TF. Let me see if I can clean this a little bit. Okay, I can simplify it a little bit and say, well, this is TF and this is TF and this is TF, so we have 5 TF plus TP1, TP2 and TP3. All right, I have all the information here. I just need to do a little bit of unit conversion. So the total time, T total, is 5 multiplied by the TF, which is 15 milliseconds, plus TP1. TP1 is 20 microseconds. If I divide that by 1,000, I'll end up with milliseconds. And 10, this is TP2 is 10, also divided by 1,000, get milliseconds again. And finally 36 microseconds by divided by 1,000 to get milliseconds. All right, quick calculations here. I'll find that. So this is the 15. Or let me do it again. So this is 5 multiplied by 15. That's 75 milliseconds plus 0.02 plus 0.01 plus 0.036. So it's 75.066 milliseconds. That's the total time. All right, so that's the answer. As I said before, you'll see this type of questions in different forms, sometimes more details about the header of the packet, the size of the header, I mean, the whether it's IP or Ethernet or both, if you are taking the data from the upper layers and encapsulating, so you have to add the headers for each layer. But this is the general approach. I like to use the drawings here, but you can also, if you can, the drawing will explain things better, but you can also calculate things directly just by understanding that you need to have the whole time from here to here, from here to here is the propagation time plus the transmission time. And then after that, you need to calculate this part. So again, the propagation time and the transmission time. And then finally, once you get rid of or you handle the first two packets, then the remaining packets like this. If sometimes there's an added complexity where you can the question says, well, we're using stop and wait. So the stop and wait means that you have to consider that you are waiting for acknowledgement. So if you have the two stations here, then you have a packet or a frame, then an acknowledgement, then another frame, and so on. So the total time will include this part here up to here for each packet, right? For each frame. So TP here, or if you look at it from this side, this is a TP, this is a TP, and this is TF. So to send one frame, you need 2 propagation delay plus 1 frame time, ignoring, of course, or assuming that the acknowledgement is negligible. So that's for 1 frame. So if you have 3 frames, 4 frames, then you have to multiply by that number. All right, but that's not part of this question, so you don't need to worry about it. Okay, I hope this is useful. Thank you for listening to this, and we'll do some other work in a different recording.